Hello, Honor Stats. We are starting Chapter 3, dealing with averages and variation. Section 3.1 is going to deal with measures of central tendency, which are mode, median, and mean. Our focuses are going to be compute the mean, median, and mode from raw data. We're going to interpret what the mean, median, mode tell you. We're going to explain how the mean, median, mode can be affected by an extreme data value. We're going to learn what a trimmed mean is and how to compute it. And finally, weighted average. First, the mode. The mode is the most common data piece. It's the data piece that appears most often. So you don't have to put the data in order to find it. So if you look at all of these particular data pieces, let's go to blue, we see that there's 1, 2, 3, 4, 5 fours. 1, 2, 3 threes. So therefore, the most common data piece is a 4. So the mode of this raw set of data is 4. Please note, if all the data pieces are different, meaning there's 10 data pieces and they're all different numbers, their mode would be no mode. Let's say in this particular example, there were 2 more 3s, which gives us 5 3s and 5 4s. Your mode would be 3 and 4, okay? So you can have more than one mode. You can have one mode. You can have no mode. The second central measure of central tendency is the median. Well, one thing you have to do with the median is you have to put all of the values in order from smallest to largest. Okay, you just learned how to collect data using a stem and leaf. So you would use a stem and leaf, you would collect the data, and then you would organize the data. This is if there were a lot of data pieces. The median is the middle data piece if you have an odd number of numbers. So think about it. If you have 5, 7, 9, 11, and 13, 5 data pieces, the 9 would be smack dead in the middle. This would be your median. But if there's an even number, 5, 7, 9, 11, 13, and 15, then you say to yourself, okay, well, we got 1, 2, 3, 4, 5, 6 pieces of data. Chop off 2 in this direction, chop off 2. You're left with 2 numbers, 9 and 11, and you have to average them. 9 and 11 is 20. 20 divided by 2 is 10. The median of this example would be 10. Here's another example. What do barbecue flavored chips cost? According to Consumer Sports, the prices per ounce in cents are here. So they already put them in order for you. 19, 19, 27, 28, 18. Oh, they didn't put them in order, sorry. You put them in order. So 18 comes first, then the 2 19s, a 27, a 28, and a 35. There are 6 data pieces, so therefore we'll chop off the same amount from both ends. And we see that we have a 19 and a 27 left over. And what we do is we average them, and the final median is 23 cents since it was dealing with price per cents of these particular chips. And the third most common measure of central tendency is a mean. Mean is what you guys consider an average. All these are averages. Mean, median, and mode are all averages. The mean is what you think of when you take an average of all your test scores or your quiz scores, etc. You add all of your data pieces and you divide by the number of data pieces. So, example, to graduate, Linda needs at least a B in biology. She did not do very well on her first 3 tests, however, she did well on her last 4. Here are her scores. Compute the mean and determine if Linda's grade will be a B, 80 to 89, or a C, and so on. So here's her test scores. What are we going to do? We're going to add them all together. In doing so, you get 560. Divide by the total number of tests, which is 7. Comes out to give us a nice 80. Therefore, Linda will get a B. Okay, so add all the scores together, divide by the total number. So I just want to talk about this because of terminology. For the mean, if you're dealing with a sample set of data, where we have, that means sample statistic, this is called an X bar, X bar, X bar. X bar is the mean. It's the symbol for mean. This E looking thing is called a sigma. Sigma means sum. That's why you add all of those numerators. The X is the data pieces. N is the total number of data pieces. But if you're dealing with a population, data from a population, then this Greek symbol is mu. That Greek symbol mu also means mean. And you see the numerator is still the sum of all of the data pieces, and they use a capital N for the number of data values in a population. Lowercase n, data values in a sample. Capital N, data values in a population. So symbolically, it's all the same, it just looks a little bit different. So I talked in the beginning about how these three can be affected by a large or very small value. A disadvantage of the mean is it can be affected by exceptional values. A resistant measure is one that is not influenced by extremely high or low data values. The mean is not a resistant measure. So if you think about it, guys, if you have all of your data pieces and you have all test scores that are around the 70s, and you get one test score in the 100s, when you compute the mean, your average is going to go a lot higher. So that 100 is considered an exceptional value, and it's going to make your test score, your average, go up. But if you think about a median, right, and you have 75, 77, 78, and 79 as your values, and you throw a 100 in there, well, your median is going to be 78. If the 100 wasn't there, your median would be the average of those two, which would be 77.5. So the addition of the 100 really didn't affect the median very much. And think about the mode. If you just add another number, whether it's very large or very small, it's not going to affect the number that appears the most often, okay? So that's an idea of how the mode, median, and mean are affected by exceptional values. Now, a trimmed mean. Sometimes we use a trimmed mean when we do have some data pieces that are exceptional. Let's say we have a couple exceptional large and a couple of exceptional small. We kind of want to get rid of them. And in doing so, we do what we call a trimmed mean. There's a 5% trim mean, and there's sometimes a 10% depending on the data pieces. And all you're going to do is you're going to order the data from smallest to largest. You're going to delete the bottom 5% of the data and the top 5% of the data. So think about it. If you have 100 pieces of data and you multiply by 5%, you get 5 pieces. So if you have 5 pieces to the right and 5 pieces to the left, you still have 90 pieces in the middle. So when I say trim, you want to get rid of these 5, you want to get rid of these 5, and then you're going to find the mean of the remaining 90 pieces of data, okay? And that's what they're saying right here. So I gave you a nice example with 100 pieces of data. So if you're asked for a trimmed, if I ask for a 10% trimmed, you take 10% off of left, that's the smallest data pieces, 10% off of the right, which is the larger data pieces, and compute the middle 80% of data pieces. I'm going to read over these and I'll show you some nice pictures. In general, when a data distribution is mound-shaped, which we call symmetrical, the values of the mean, median, and mode are basically the same or almost the same. For skewed left, the mean is less than the median, and the median is less than the mode. And I'll show you why here in a second. For skewed right, the mode is the smallest, the median is the next largest, and the mean is the largest. So understand what skewed right is, and mean, and understand skewed left and mean. Let me show you real quick here. So if it's symmetrical like this guy right here, the data pieces are going to be, the measures of central tendency are going to kind of all be right smack dead in the middle. Mean, median, mode are going to be really, really close to each other, if not exactly the same. Now, skewed left, remember, when the data pieces, the smaller pieces over here to the left, it's called skewed left. Notice that the mean always goes towards the skewed side, towards the tail. So the mean is going to be smaller. The median is going to be next. And notice the mode is going to be located in the largest building. That's where the most data pieces could be that are the same. Now, what about skewed right? Notice the mean goes towards him. So the mean always goes towards the skew side. So in this case, the mean is going to be larger. In this case, the mean is going to be smaller because it's going towards the smaller pieces. And then we have the median. And again, notice the mode is going to be in the big building, more of a tendency of being within those particular values. Okay? And finally, a weighted average. Sometimes we wish to average numbers, but we want to assign more importance or weight to some of the numbers. Suppose your professor tells you your grade will be based on a midterm and a final exam, based on 100 possible points. However, the final exam is worth 60% of your grade, and the midterm is 40% of your grade. We want to do a weighted average. So technology terms for us, it's the sum of each data piece times its weight divided by the sum of the weights. Okay. So therefore, looking at this same exact problem thing, you got a midterm of 83 and your final exam was a 95. Remember, it's 40% for midterm and 60 for final. We take, well, let me go back to the, so remember the midterm, you got an 83 and we're taking 40% of it. It's a sum, so we want to add. 95 is what you got on the final, and we got to take 60% of the final. This right here should always add up to give you 1 when you're done with a class. Let's say you're not done with something, you can still average. Let's say you have 30% quiz and 40% tests, and your homework is not done yet. You would still take 40% of the test, 30% of the quiz, and this would be 40 plus 30 down here. But in doing so, guys, working this particular problem out, you get 90.2. Therefore, you earned enough to get an A. Okay? So that's the last thing that we want to do with chapter 3.1.